Howdy, today I'm Flippin Science looking at yield conditions and flowcharts. So the science understandings we're going to look at designing chemical synthesis processes involves constructing reaction pathways that can include more than one chemical reaction. Steps in chemical processes can be displayed in flowcharts, and industrial processes are designed to maximize profit and minimize impact on the environment. So to industrially produce a chemical, normally there are multiple reactions that have to occur to produce your final product. We're going to have a look at sulfuric acid production a little bit later, but we can see here's a bit of a flowchart showing the manufacturing process. There's lots and lots of small chemical reactions that all add up finally to the production of sulfuric acid from sulfur and oxygen. You don't just stick those two together and get your sulfuric acid, you have to do a whole heap of other reactions to produce it eventually. So let's have a look at some flowcharts. 3, 2, 1. Next bit we're going to look at is flowcharts. You need to be able to look at a flowchart and see if you can determine what's going on in terms of raw materials, products, chemicals that are present at particular stages and so on. So a flowchart, really, you follow through, you answer certain questions, or in terms of chemistry you just kind of follow the system through and see what's coming in and out at particular times. The best way to learn about flowcharts is to look at them and see what's going on. So let's have a look at this flowchart which is producing biodiesel. So here's the biodiesel over here. So this is our final product, and you can kind of see the arrows in the end point here or in a few other directions. And that tells us where our products, byproducts and waste products are going to be. Arrows coming in indicate substances that are being added into a mix. So our raw materials in this case are a catalyst, methanol and vegetable oil. Now we haven't been told what the catalyst is, so that's not going to be very helpful. Often in these they would have catalyst maybe even over the arrow so you know what the catalyst is. But our raw materials at least are methanol and vegetable oil, we can tell that, and the catalyst as well. If we follow through, if we look in this block here, what we would have here is a mixture of the catalyst, methanol and vegetable oil. Because they've all been introduced previous to this point, so that's where they'll be. Then things are separated and we follow through and we can see we've got a waste product down here which is discharged, which is wastewater which is neutralized. That's produced from this purification step up here that comes through here. So that's a waste product. If we have a look through, we've got another byproduct here. So we've got glycerin, and glycerin might be refined to produce glycol. Glycol could be ethylene glycol or something like that. So this is a byproduct if it's being produced, turned into something that's useful. And if we look through, we can see our final product is biodiesel, so that's our product that we want. Here's another flowchart. This is for the production of biofuel from cellulose. So raw materials, up here we've got wood chips, so that's one thing that's added. And it's already in here a mix, we've got some bisulfite or acid that are in there. If we follow through, we can see we get some filtration, some firing and so on, saccharification, so that's turning into a sugar. Then we have fermentation, which is handy, and then that leads into distillation and the ethanol. But we get products from the fermentation, such as, here we've got heat and chemicals. It doesn't say what the chemicals are. But they're circled back into the system, so that means that we're not getting a waste product there. We can see some waste products though. We've got lignosulfonate down here. That doesn't seem to be going back into the system anywhere else. So the lignosulfonate, I think that's a waste product. Hemicellulose is produced from filtration here and some reverse osmosis. They can be fed back in and fermented again. So these hemicelluloses are a byproduct, and then they feed back into the system to produce more ethanol. So there's some examples of reading a flowchart so I understand what's going on. In any industry you want to have the maximum output with the minimum outlay. So that means you want to make the most you can for the cheapest price. So in chemical industry this means you want to make the most product in the shortest time at the lowest cost. In chemical industry, the companies, they find a balance between the yield of the product and the rate of formation, so that they can make the maximum amount of product in the shortest amount of time and save themselves as much money as possible. So an example of this is the Haber process that produces ammonia from nitrogen and hydrogen. Here's the equation down here, and we can have a look at the equation and figure out what would be the situation that would produce the maximum yield. And we're going to look at that in terms of temperature and pressure. So if we look at pressure, if we increase the pressure on this system, we'll have more molecules bumping into each other, and we'll get more successful collisions for reasons that we've talked about before. But if we increase pressure, we'll also improve our yield. We'll produce more product. And the reason for that is if we increase this pressure on the system at equilibrium, we have fewer molecules on the right-hand side of the equation than we do on the left. So on the left-hand side, we've got 4 molecules. On the right-hand side, we've got 2. So if we increase pressure on this system, it will shift to the right to relieve that pressure. And that means we make more ammonia, which is more of what we want to make. If we look at temperature, though, because the forward reaction, so the one going from left to right, the forward reaction is exothermic. To get the maximum amount of ammonia, we'd want to push the equilibrium in the exothermic direction, and we do that by cooling it down. So if we cool down this system, it would shift to the right to favour the exothermic reaction, and that would produce more ammonia. So to maximise yield, we would increase pressure and reduce temperature. But this isn't what happens in the real world. So in the real world, the reaction happens at 400 degrees Celsius and 250 atmospheres of pressure. So a moderate pressure and a moderate temperature. By increasing the temperature, the payoff there is that you get more product in a shorter amount of time because you have more of those collisions between the molecules and therefore more successful collisions. And again, for reasons that we've talked about before. So the pressure is higher to make more ammonia, but the temperature is higher to make more ammonia in a short amount of time, but you don't get the maximum yield from your reactors. So in this case, we get 45% of the yield. So this is an example of that compromise. So if we had it even higher in pressure, that would cost more money because it costs money to provide the energy to put gases under pressure, and also in terms of safety, you need to have specialist equipment to have higher pressures. If the temperature was too low, then the reaction would happen very slowly and you wouldn't be able to make enough ammonia to make the costs worthwhile. You wouldn't be able to make a profit. So by heating it up, you increase the reaction rate. Even though you decrease your theoretical yield, you still get more product in a short amount of time, so it's worthwhile. So another example of a process like this is the contact process that's used to produce sulfuric acid. You do that by roasting a metal ore that contains sulfur and oxygen, and that produces sulfur dioxide. Sulfur dioxide reacts with oxygen, produces sulfur trioxide. That sulfur trioxide reacts with previously made sulfuric acid to produce oleum. Then the oleum is diluted with water to make more sulfuric acid. The main step here is this step here, and we're going to talk about that in a bit of detail. Another interesting thing is that this reaction is catalyzed by the use of a vanadium pentoxide catalyst. It's very important to remember that catalysts won't change your position of equilibrium. They won't produce more product or more reactants, but what they'll do is you'll get to your equilibrium position faster. So they get you to the equilibrium position faster, but they don't affect the concentration of reactants or products at equilibrium. So like I said, this is a key step, and we need to look at this and determine what conditions would maximize the yield. So in terms of pressure, if we increase the pressure, we're going to shift the position of equilibrium to produce fewer molecules. So in this case, increasing the pressure would produce more sulfur trioxide, which is what we want. There's 3 molecules on the left, 2 molecules on the right. So if we increase pressure, we would get more sulfur trioxide produced. Then we need to think about temperature. And similar to before, because the forward reaction is exothermic, if we want to make the maximum amount of product, we want to favour the exothermic reaction by cooling down the system. If we cool down the system, we're going to favour the exothermic direction. In this case, it would be forward. So by removing heat energy, we'll favour the production of sulfur trioxide. So the best conditions here would be high pressure and low temperature. But again, if we look at what happens in industry, they don't do that. The temperature they do this is about 400 degrees, which I think I had here, 450 degrees. And the pressure, they don't increase the pressure at all, they keep it at atmospheric pressure. And the reason for that is the gain in yield by increasing the pressure isn't matched by the cost of producing a high pressure system to produce more sulfur trioxide. So because increasing pressure increases the amount of energy required, and energy costs money, doesn't matter really where it comes from, it's just not worth it economically to increase the pressure on this system. Again, cooling down, that will increase your yield in this case, but also reduces the reaction rate. So not enough sulfur trioxide would be produced in a timely manner to make it profitable. So instead they increase the temperature to increase the reaction rate. They'll get a certain amount of sulfur trioxide, never the maximum yield, but enough to make a profit. So to summarize, it's an advantage for a manufacturer to produce their product at low temperatures and pressures where possible. The reason for that is it reduces your overall costs, and particularly energy costs, since it requires energy to produce high temperatures and high pressures to start with. The other aspect, though, is that having high energy costs also has a high environmental impact. The reason for that is usually energy is coming from the combustion of fossil fuels. That leads to an environmental impact in terms of the enhanced greenhouse effect that we talked about a while ago. So by burning fossil fuels to provide the energy to either heat up or add pressure to a system, that's having a big impact on the environment. Where possible, catalysts are used, since you can reduce your energy costs because you don't have to provide as much energy in terms of temperature or pressure for the reaction to occur in an economical fashion. So catalysts are used if possible, and so on. So today in Flipping Science we looked at synthesis pathways, flowcharts, and compromise for manufacturers. That's it for Flipping Science today. See ya.